Welcome to Engineering Studio with Dr. Mohammed Tahir. In this video, we are going to discuss about the procedure for design of steel beams. Okay, first of all, we need the known data, for example, the span of the beam and the applied loadings. Okay, once we have the known data, mean the span, the loading, then we need to estimate the self weight of the member. At that stage, as we have not designed the member and we do not know the section of the member, so we cannot exactly calculate the self weight of the member. So we need to approximate the value of self weight of member, and we can approximate the value of self weight by using three guidelines. So the self weight may be taken 10% of the applied dead UDL or dead point load distributed over the complete length. For example, if we have a beam and a uniformly distributed load of 10 kilonewton per meter is acting on this beam, so we can take the 10% of this, mean 0.1 times 10, so it will give us 1 kilonewton per meter. So the self weight of the beam will be taken as 1 kilonewton per meter. But if a point load is acting on the beam, for example, a point load is acting on the beam and the beam has a span of 10 meter and the load is equal to 10 kilonewton, 100 kilonewton of load is acting on the beam. So in that case, we need to calculate the self weight, and it will be calculated as 0.1% of 100 kilonewton divided by the total span. Mean, first of all, we will calculate the 10% of the point load and then we will distribute it over the entire length. So it will give us 1 kilonewton per meter. So in this way we can calculate, or we can approximate, the self weight of the beam if dead UDL or dead point load is given. Okay, if only live load is applied, so in that case self weight may be taken equal to 5% of its magnitude. So if 20 kilonewton per meter live load is acting, so in that case we will take the 5% of this, mean the self weight will be equal to 0.05 times 20. So it will give us 1 kilonewton per meter. So in that manner we can calculate the self weight if only live load is acting on the beam. So in case only factor load is known, so in that case we can take 3% of the factor load. So whatsoever is the value of factor load, mean the combination of dead and live and their factored value, so in that case we can take the 3% of the factor load as a self weight of the member. Okay, once we have estimated the self weight, so now we know the dead load, live load, including the self weight. Now the next step will be calculate factored loads. So we need to calculate the factored loads like 1.2 D plus 1.6 L. Okay, after that we need to draw the shear force and bending moment diagram based on the factored loads, and then we need to calculate the CB for each unbraced segment. So for each segment we will calculate the CB value. Once we have drawn the bending moment diagrams, then it is easy to calculate the CB value, because CB value depends on the moment distribution or the moment values in the required segment. So we need to calculate M maximum, MA, MB and MC to calculate the CB value. M maximum is the maximum moment within the span, MA is the bending moment at 1/4 of the span, MB at the center and MC at the 3/4 of the span. After calculating the value of CB, then we need to find the value of maximum bending moment, maximum shear force and the unbraced length for each segment of the beam. So each segment mean if we have a beam and it is laterally supported at different positions, so this much portion will be considered as a one segment, then second segment and then third segment. So a segment for which the compression flange is unbraced. So for each segment we need to calculate the maximum bending moment, maximum shear force and the unbraced length. So based on these three parameters, maximum bending moment, LB and CB, mean M, LB and CB, we need to see which segment will be the most critical segment. So we need to decide the most critical segment out of all segments based on these three parameters, or these three values M, L and CB. And once we have decided that which segment is the more critical, or once we have decided the most critical segment, then we need to design for that segment, and we will select the section for that segment, and then we will check for the other segment whether the selected section is suitable for the other segments or not. So design this segment first and then check for other segments. So next is to calculate the D minimum considering the allowable deflection. So for buildings, the D minimum should be L by 22 if the steel is A36 steel. And for bridges and for other buildings, we have already defined the D minimum values in case of previous video. So assume the section to be compact without lateral torsional buckling in the start and calculate ZX. So initially we can calculate the required section modulus, plastic section modulus, based on the assumption that there is no lateral torsional buckling and our section is a compact section. So the capacity, as we know that the capacity in case of plastic section is equal to Mn is equal to Zx time Fy. So if we rearrange this equation, so Zx will become Mn over Fy. So from here we can calculate the Zx required. So after calculating the Zx required, we can select the section based on these three criteria. So Z of the selected section should be more than Z required, means plastic section modulus. The weight should be minimum, and D depth of the section should be more than the D minimum, as we have calculated in the previous step. If delta maximum required to be lesser than L over 360, like L over 500, L over 800, so in that case we need to calculate Ix required for the deflection from the deflection formula with only the live load acting, and select section such that Ix of the member or the section should be more than Ix required. So in that case, if the deflection is reduced to L by 500 or L by 800 or some other value, so in that case we cannot use the D minimum equal to L over 22 or some other value. So we need to calculate the Ix required for that section, and the section selected should have the second moment of area more than the Ix required. For that, what we will do, for example, if the beam is subjected to uniformly distributed load, so in that case deflection will be equal to 5 over 348 times WL raised to power 4 divided by EI. So from this equation we can calculate the Ix corresponding to the required deflection. So according to the limit of deflection we can calculate the I value, and then we will select the section based on this I, Zx and weight minimum. There are two methods for the selection of section from the LRFD manual. The first method is use of selection table. So selection tables are given in the LRFD manual. So from there we can select the section based on the Zx. So the procedure is enter the column headed Zx and find the value equal to or just greater than the plastic section modulus required. The beam corresponding to this value in the shape column and all beams above it have the sufficient flexural strength based on these parameters. So here we have this table. So the first column is Zx, the second column is SI shapes, and then the properties. So what we need to do, we need to enter into the first column, and we need to see the required section modulus. For example, the required section modulus is close to 30,480. So our selected section will be this one. But this section has the weight equal to 653 kilogram per meter. But if we move upward, So the sections have higher section modulus, but their weight is less. So the weight of the above section in this group is 642. So it means as we move in the upward direction in the same group, if we see, we have the group of 4 sections here, group of 2 sections here, group of 4 sections here. So in all these groups, the section which is at the top and it is represented by the bold faces, so it is the most economical section because it has more section modulus but less weight of the section. So if we select this section, so it will be most suitable as well as it will be most economical. So after selecting the section, we need to perform the checks related to moment capacity, shear capacity, deflection and the self weight. But before we move toward these checks, we need to see if CB is more than 1, so we need to calculate LM instead of LP. And if LB, unbraced length of that segment, is more than this LM value, so in that case we cannot use this section, or the section selected based on this table will not be suitable. So in that case we need to move toward the unbraced design charts. If this LB is less than LM, then we can directly apply these checks, and if this LB is more than LM, then we can neglect this section and we can proceed further for the selection of new section based on the unbraced design charts. So the next method is use of unbraced design charts to select the section. So this method is applicable in case where the above method is not fully applicable, where the section selected by the section selected from the table are insufficient or not suitable. So in that case we can use these charts, and LB is more than LP or LM. So these design charts are basically developed for uniform moment case, and CB is equal to 1. And if we see these charts, so we will have the solid circles on the lines, and these represent the value corresponding to LP, and hollow circle, this represent the value corresponding to LR. So according to MU and LB, we need to enter in these charts, and then any section represented by a curve to the right and above the point selected in number 1 will have a greater allowed unbraced length and a greater moment capacity than the required value. So we can see over here. So here we have a chart. So on one side we have unbraced length, and on the other side we have nominal capacity. And this chart is developed for phi 0.9, CB is equal to 1 and Fy 250. What we need to do, we need to enter in this chart based on the unbraced length. For example, the unbraced length is 10 and the bending moment capacity is 9000. So we need to enter in this chart. So this point will be corresponding to capacity and the unbraced length. So any line on the right side and above will be the required section. So here if we see, this line is the closest line, and the section corresponding to this is 1000 times 883. So this section will be a suitable section for our required section modulus. So in that case, in design charts we do not see the section modulus, we only focus on unbraced length and required moment capacity and select our section. And if we see over here, so we have these solid circles, and here we have this hollow circle. So for this section, for our selected section, this is solid circle and this is hollow circle, and our point is in between these two circles. So it means our section will be in inelastic lateral torsional buckling range, and if our selection is in this range, so in that case our section will be in plastic stage, and if it is in this range, so it will be in elastic stage. So what we need to do to select the section, we will enter into this chart based on the unsupported length and bending moment capacity, and any section right to it will be selected. So this section will be selected. A dashed line section is not an economical, so sometime in this chart there will be some section with the dashed line, for example over here. So this section will not be a economical section. So if During the selection, we encounter this dash line, so we need not to select the section corresponding to that dash line. Rather, we can move further in the upward direction and select the section based on the solid line. Select the corresponding section as the trial section, and it will be the lightest available section for the requirements. If CB is more than 1, because these charts are based on CB is equal to 1, but if in our case the CB is more than 1, then we need to calculate the M required by dividing this MU by CB, and then select the section based on this MU required and unbraced length. Instead of just MU, we need to divide it with CB, and then we need to use this chart to select the section. Okay, after selecting the section, either it is based on the table or based on the chart, so we need to perform the checks. The first check is compactness check or internal stability check. So we need to see these three conditions. The web is continuously connected with the flange. Flange stability criteria mean lambda of flange is less than lambda p, and web stability criteria lambda of web is less than lambda p for web. So if any one out of the above three is not satisfied, then we need to revise the section, because in this case we are only dealing with the compact section, so we need to satisfy these three conditions. Okay, after that we need to calculate LP, LR and LM, or we can select this value from the properties table, and after that we can calculate the bending moment capacity, and MU mean the applied bending moment should be less than the bending moment capacity phi b mn, and this bending moment capacity is based on the unbraced length. So we need to compare this unbraced length with LP and LR, and correspondingly if the buckling is elastic, inelastic, or there is no buckling, then based on that conditions we need to calculate this moment value or moment capacity. So after that we need to perform the shear strength check, that VU should be less than phi Vn. Then we need to check the deflection. The deflection actual should be less than deflection allowed. Then we need to check for the self weight, and actual self weight of the member should be less than 1.2 times the assumed self weight. So the actual self weight can be only 20% more than the assumed self weight. If it is so, then it's okay. Otherwise, if the actual self weight is more than this value, we need to revise our section based on the new calculated loads. And then if all these checks are satisfied, then we can write the final section, that it is a section which can satisfy all the requirements. And again, this section was for one segment or for the critical segment. After that we need to perform all these checks for the other section. We need to perform the capacity check, moment capacity check for all other sections or for all other segments.